Good afternoon. My name is Mark Overby from NVIDIA, and I'm here to give you a presentation today about GPU attestation for confidential compute, what attestation means for a GPU in terms of confidential compute, the attestation architecture that we support, and we'll be going through some basic concepts of attestation. So as I mentioned, we'll talk about, what is attestation? Why is attestation important? So in other words, why does this matter in terms of your confidential compute workloads? What are some key aspects and participates in the entire attestation flow? And then we'll talk specifically then about how the GPU attestation is done, how it's done in a trustful manner, what we attest to, and then we'll also discuss a roadmap of attestation-related services and other things that will help you with attestation and your confidential compute workflows for availability now as well as availability in the future. So first, let's talk through why is attestation important. So attestation is basically the act of proving in a trustworthy manner that the configuration of the device is what you expect it to be and that it is in the configuration that you need it to be in order to properly secure your workloads. So the GPU does provide secure boot. And so a lot of times, the question is, well, why do we need attestation in addition to secure boot? So secure boot merely tells you that the software you're running is authentic and that the software that has been processed has come from an official source. What it does not tell you, though, is there a configuration question or is there a configuration option that has been set correctly to handle a confidential compute workflow? So for us, as an example, on the NVIDIA GPUs, we have multiple configurations. Some support confidential compute and some do not support confidential compute. So the attestation allows you to differentiate between those two, even though the secure boot software is the same software. So that allows you to differentiate between a confidential compute configuration and a non-confidential compute configuration, both of which are authentic secure boot configurations. So the attestation then will prove to you that the workload that you have that needs confidential compute can run in that configuration with the security claims and guarantees that are made by confidential compute. The same attestation techniques that we're talking about here for the GPU, you also do for the VM itself that's running on the CPU. The VM can also use attestation to prove to either some piece of software running inside the VM or a piece of software outside of the VM that the VM itself is also in a trusted compute configuration. And so when you combine those two attestations, then a relying party, and we'll talk about relying parties upcoming here, then your relying party will be able to determine that both entities involved in processing this workload are in their confidential compute mode and that they are ready to go. And we talked about the remote entities there. So as an example of a configuration here, a remote entity may be the safeguard of the keys that protect certain data or the data itself or both. And it can decide to release the keys and data to the VM based off of the attestation of it and its GPU acceleration. So there's many participants in an attestation workflow. The attestation, in the technical terms, is the process of taking evidence provided by an attester, verifying that evidence against a set of reference values and endorsements, and then that leads to an appraisal, which leads to an attestation result, and then a relying party can take some action or enforce policy based off that attestation result. There's a lot of terms in here and a lot of different parties, and we're going to go through each one of these, and we'll discuss where NVIDIA provides what in terms of GPU attestation. Just to mention, this picture comes from an RFC called 9334, or the Remote Attestation Procedures, or RATS architecture. So you may hear me refer to RATS as we go forward, and that is this architecture. So the first piece is that in this diagram, and going through here, the parts that are shaded in green are parts that NVIDIA supplies, and parts that are shaded in gray will be parts that either the trusted virtual machine owner or the trusted workload owner provides, or it could be another third party that provides that. In the first part, the GPU Security Enclave, inside the GPU is an internal root of trust. So that internal root of trust is a highly secure enclave within inside the GPU that has cryptographic protections to maintain sets of keys and also collect measurements of other parts of the system. So that GPU Security Enclave acts as an attester because it collects evidence. So it will measure configuration, it will measure software, it will measure other values that track to what confidential compute is all about. The endorser is also part of that security enclave. The endorser basically is signing those signing those. So the first couple of components we'll talk about here are the endorser and the attester. So inside the GPU, there is a GPU security enclave that is a highly secure environment that maintains cryptographic keys for doing digital signatures. And then it also maintains the ability to do measurements of the rest of the platform. So that rest of the platform can include the configuration. It can also include the measurements of the software, measurements of firmware, and other interesting information that determines whether or not you are in a confidential compute configuration. So the attester portion of the internal root of trust, or the GPU security enclave, collects that evidence. That evidence is those measurements of the various things that I've mentioned. It also acts as the endorser. Now, because it is a highly secure environment that has cryptographic keys and the ability to do digital signature, and that is an isolated environment that is not penetratable by other portions of the software or the hardware, it can then securely sign that information so that when it leaves the attester and passes to a non-secure environment to go into the verifier, that information can be guaranteed to have come from a valid attester, and that it's fresh, and that it hasn't been tampered with by somebody before the verification happens. So we also provide an infrastructure to verify the endorsements through standard certificate chains. So we have an X509 certificate chain that chains all the way up to a certificate authority, and that will validate all of the cryptographic links in the chain all the way down to the attester. So NVIDIA also provides what we call reference manifests. Reference manifests are basically the way you know that a specific measurement is a valid measurement, and that when you measure against this and compare it to the reference value, so when you take your evidence in the verifier, compare it to the reference values, if those comparisons match, then you know that the GPU is in a confidential compute state, and that confidential compute state has been attested to and claimed by NVIDIA to be secure. So those reference values today are provided in what we call reference integrity manifests, or RIMs. So those RIMs are distributed, and they're used by the verifier to compare the evidence against an appraisal policy. And we'll talk about the appraisal policy next. But those reference values are also digitally signed. So they're also what we would call endorsed. Those endorsements also go through a certificate chain all the way back up to a certificate authority. And so those are part of a digital signature mechanism as well. We'll talk a little bit later about how revocation happens, but they are also revocable, so that in the future, if there is a problem with a reference manifest, or if there's a problem with an attester, those can actually be revoked so they can be known to not be trusted any longer. So appraisal policy, NVIDIA provides a reference appraisal policy as well as a reference verifier. So the reference verifier that we provide is a local verifier that would run inside the trusted virtual machine. That verifier has an appraisal policy where it examines static values as well as dynamic values and ensures that the combination of those two match reference manifests and that the values are consistent with being in a confidential compute environment. If those appraisal policies pass, we will provide an attestation result that indicates that it has been compared against a valid reference value, that the endorsements have been checked on both the reference values and the attester, and that that entire chain has been proven to be in a confidential compute configuration. It is also possible to create a remote verifier. So you are not limited to a local verifier. You can also use this in remote verification. The difference is that the evidence, the endorsements, the reference values, and the appraisal policy would all be going to an entity outside of the trusted VM. But because the evidence and the reference values are endorsed, there's not a security problem with moving it outside the VM. And depending on your threat model, you may choose to have a remote verifier just because you may not have built enough trust in the virtual machine itself to do the measurements necessary. So the last thing we'll discuss here is the relying party and their use of the attestation results and the appraisal policy for the attestation results. NVIDIA does not supply this because this is up to the person who owns the confidential compute workload and who owns the data and who owns any necessary cryptographic keys to unlock the data. They can determine what policies are necessary in order for the attestation results to be considered valid, and necessarily, too, what combination of attestation results may be necessary to unlock the data. As I discussed previously, the virtual machine also uses an attestation flow, and the relying party owner could have an appraisal policy that basically says, I need both the virtual machine and the GPU to both give me positive attestation results before I will unlock the data. And that's the appraisal policy that you would set. The relying party is the person who's actually going to be doing the decision on what data to release and what keys to release. And so you would combine multiple attestation results along with the appraisal policy, and then you would determine that it is safe to unlock the data. So now that we've gone through kind of the high level of all the participants in it, let's talk a little bit about the details of the attestation sequence. So not every exact step is listed in this sequence. This is still a little bit of a high level diagram, but it gives you a little more detail about what happens now under the hood. So in the confidential compute VM, through libraries that we provide, an SPDM get measurements call happens to the GPU. So the GPU will then return the endorsed evidence. And as I discussed in the previous slides, that happens through the secure enclave that's inside the GPU. Now, there's two options, as I discussed before, in verification. There's a local verifier and a remote verifier. In the local verification, the endorsed evidence will go to your local verifier. It will check the endorsements. It can reach out to an OCSP service to check for revocation on any of the certificates involved in the endorsements of both the reference manifest and the evidence itself. Once it's determined that everything has not been revoked, then it will also check the reference manifest, ensure that the evidence matches the reference manifest, and then it provides the attestation results back to the confidential compute VM. So the remote verifier is very similar. The only difference now is I'm providing the data out to a remote verifier, and it's doing the same actions. It's just doing it remotely as opposed to being inside of the trusted VM. One of the things that's not shown in the diagram here is part of the get measurements call and the evidence call is there's a freshness nonce that's created. If you're using a local verifier, the nonce is created locally inside the VM and is provided as part of the measurement generation and the measurement endorsement. So once you have that, then the verifier knows that the data that it's examining for verification isn't stale, that was captured by an attacker at some point in the past, and does that. So our software allows you to either generate randomly inside the VM, a nonce that's passed in there, or if you're in the remote verification case, you may want the remote verifier to actually be the entity that you want to generate the nonce because it's the one doing the verification. So a step that's not shown in here is you could see a nonce going from the remote verifier to the confidential compute VM, and then the SPDM get measurement starts, and then the flow remains the same. Once you've gotten your attestation results from either your local or your remote verifier, you pass those attestation results to the data holder, or in another term, the relying party, and then it would release keys, data, or both keys and data to the confidential compute VM, and then the VM then starts passing data and keys to the GPU. So once you've established the initial session, which happens before attestation here, you know that all of the data that you are passing back and forth to the GPU is being protected with AES GCM. So all of this happens with a protected configuration. So when you start your workload, you know that the workload has been protected, and then SPDM itself has its own security around ensuring nobody has tampered with the SPDM workflows. So now let's start to dig in a little further and talk about the various attestations and what we call attestation time domain. So the attestation time domain is a period of time in which the attestation is guaranteed not to change from the point where you measurement until the end of your session. So if you have a time domain of some piece of attestation that goes from session start to session end, or reset to reset, you can measure it once and know that you can rely on that. So that is a security claim that would be made by the entity that is collecting the evidence. So in our case, the GPU Security Enclave is guaranteeing that anything that we tell you that has an attestation time domain of full session to session or reset to reset, you can measure once and rely upon going forward. Dynamic attestations have a time domain of less than reset to reset. So a dynamic attestation may change over time. Now, depending on your security model, you may choose to deal with that in terms of measuring it frequently or you may choose to measure it once at the beginning of your session and then rely on the fact that the dynamic changes in there will not affect your security model. And we'll talk here in a moment about, for the GPU, what attestations do we have that are done with a long time domain or a session-to-session time domain or a dynamic time domain. But I wanted to introduce the concept of a time domain before we begin talking about it. So what do we measure? So there are what we call measurement groups, or various buckets of things that get measured. And we've broken this up here into ones that have a static time domain, which is the life of the session, or a dynamic time domain, which is something that has a lifetime that is less than from your session start to your session end. So in the static group, we have static hardware configurations. So these are things that would be configured either during manufacturing or in a post-manufacturing process, but that are immutable and never change. So examples here would be things like fuses for security settings on debug, enable, or disable, microcode revocations, confidential compute enablement, whether the part is capable of confidential compute, and features of the GPU itself. The next category down we would talk about is things along the lines of firmware or vBIOS. So these are all software components that are flashed into an external EEPROM on the GPU. All the firmware loaded from the vBIOS, the execution environment of the vBIOS, all the device initialization data tables, all of that firmware is measured by the roots of trust. The root of trust then keeps those measurements around and endorses it later as part of the attestation. Driver microcode. Driver microcode is very similar to firmware. The difference is microcode is loaded by the drivers running on the CPU, as opposed to firmware that is loaded autonomously from the GPU through the through the EEPROM or things similar to that. So those microcodes are loaded from the PF is the physical function driver package. So the signature and execution environment of all the microcode for engines, such as the downstream security enclaves beyond the initial root of trust, all of those are measured and made as part of the attestation measurement. We also look at hardware initialization states. So hardware initialization states would be anything that's initialized by the vBIOS, the physical function driver, or things initialized by the security enclaves. These would also be configurations necessary to establish your hardware trusted execution environment inside the GPU. So this would be configurations like our PCI Express firewalls that keep the hypervisor or other entities from being able to tamper with or examine data or change the configuration of the GPU. It would be the state of debug interfaces. So we do support in confidential compute mode what we call a production mode and a development mode. In the development mode, there are still types of debug and high resolution timers and things like that that are enabled, which makes it useful, but it may not be necessary for the security posture of your data in a production environment. So it allows you to develop your software, get your software ready. You can use test data that's non-confidential to ensure that your entire platform is ready to go in a confidential compute manner, but it doesn't expose your actual data. Then if you're in a production configuration, you know that all of the security claims are valid at that point and that you can use your actual live data in that configuration. And the attestation will be able to tell you the difference between when you're in a confidential compute production mode versus a confidential compute development mode. Also, other various hardware engines, whether or not they've been programmed to be in their hardware security mode or their non-secure modes, those are all measured. The resource isolation between trusted execution environments. So, looking forward when there's a MIG configuration, and each MIG is its own security enclave or trusted execution environment, this would also ensure that the resource isolation has been properly set up between the various MIGs. Now we'll talk a little bit about one of the dynamic states. So dynamic states may be software engine states that are programmed by drivers or other software. So this, would be things that are not necessarily, part of the base security configuration, but may affect the overall posture of the platform. And so these would be things that are programmed as part of the runtimes, and these we measure as dynamic states. The last piece of static data we have is what we call other reported information. This is kind of a catch-all category. And it's plain text, so it's not hashed or anything like that. It's just information that is captured, and this assists the various attestation report verifications. So this would be things like the size of the security memory enclaves, or what SKU it is, the MIG states themselves, what driver versions or vBIOS versions are running. And then there's also an event log that's captured as part of that, so that when things happen or when various security events may occur, that event log is captured as part of attestation to ensure that it is properly signed, sealed, and provided to the trusted VM in order for them to examine it, and it can also be part of the verification. So now let's talk a little bit about our attestation services in terms of what will be available today or available at the Hopper Confidential Compute launch this summer, and what we'll be providing as a follow-on to that over the next year beyond the Hopper Confidential Compute launch. So the first thing we're providing, obviously, is the GPU attester itself. The GPU attester is the hardware that I talked about. That is the secure enclave inside the GPU, along with the root trust of measurement, the root trust of reporting, and that combined allows us to generate that evidence and endorsement that we talked about previously. We also provide endorsement certificate chains. Those endorsement certificate chains are the necessary certificates that start from our certificate authority and run all the way down to the identity device inside the hardware itself. The next thing we provide are RIM bundles, or what we call reference integrity manifest bundles. Those are provided with the driver builds during the launch process. Those RIM bundles are used by the verifier itself in order to do the verification and compare the verification to the evidence. We also provide an attestation SDK. That attestation SDK allows you to trigger attestation, to generate new nonces, to regenerate attestation as necessary, and to take the evidence and provide it to a verifier of your choosing, or you can provide it to the local verifier that we supply. The local verifier itself, as I mentioned before, will be open source this summer. It's not currently open source, but we do provide the local verifier. It's also adaptable to non-local uses, so you could take the local verifier and port it into a remote verification environment. The other service we provide at the launch of Confidential Compute will be our OCSP service. So for those that may not be familiar with that acronym, that service is a service to check the certificate status of any certificate. So the certificates that are used for endorsement, the certificates that are used for the RIM bundles, all of those can be checked through OCSP to make sure that we haven't had to revoke them for some security reason or because of some other fault. So that's what's available today or will be available at the Hopper launch this summer. But let's talk a little bit about other enhancements that will be coming in the future. So NVIDIA will operate and provide a remote verifier service. We expect that to be based off of some industry standards, but we will be providing that remote verifier, and that verifier will follow the same open source policy as our local verifier, so that if you're using our remote verifier service, you know what code is running, and you can ensure that you can trust that code. We will also be providing an attestation brokerage SDK. So that attestation brokerage SDK allows you to take multiple attestations, combine them together, and provide an overall attestation for environment. So this is especially useful in a multi-GPU environment. So a lot of what I've talked about here is kind of the single GPU configuration. In a multiple GPU configuration, you would want to take the attestations from all of the GPUs that you are attached to or that are part of your environment, and you would want to measure and verify each one of those. The relying party may want to see that all the GPUs have been verified as well as all the virtual machines. The attestation brokerage SDK allows you to combine a set of disjoint attestations, combine them into an attestation that represents the overall system, and then that attestation broker then also signs that as its own unique entity attestation token. The next service that we'll be providing in the future is an on-demand reference manifest distribution service. So today we provide the RIM bundles with the driver builds. In the future, there will be an on-demand service that you can call up and basically say, I need the RIM bundles for this driver release or for this product and driver release, and it will provide those RIM bundles to you on demand, as opposed to having to cache all of them locally or pull them out of the driver builds as you receive them. The RIM bundles we provide today are based off of the TCG and NIST RIM standards. We will be moving to the IETF-based co-RIM, co-SWID, and co-MID based reference values in the future, and that will be an enhancement that will come later